So we begin the fourth module on Fourier transforms. So we leave for now the study of Fourier series and we take the other aspect of Fourier analysis, namely Fourier transforms. Now recall from basic ODE theory, how do you solve ordinary differential equation with constant coefficients, a linear kth order ODE with constant coefficients. For example, let us look at a second order linear ODE with constant coefficients, y double prime plus ay prime plus by equal to 0. The method is very clear from your undergraduate courses. You feed a special solution e to the power mx into the differential equation. What do you get? From the y double prime you are going to get m squared e to the power mx. Ay prime is going to give you am e to the power mx and by is going to give you b times e to the power mx. E to the power mx is never 0. So if this e to the power mx has to be a solution of this differential equation, compulsorily m squared plus am plus b must be 0, or m must be one of the two roots of the quadratic polynomial m squared plus am plus b equal to 0. This quadratic polynomial, as you know, is called the characteristic polynomial. So more generally, if we have a kth order ordinary differential equation, then what's the story? You're going to get a kth degree polynomial in M, the characteristic polynomial. If this polynomial has roots m1, m2, mk and they are all distinct, then e to the power m1x, e to the power m2x, etc., e to the power mkx is the complete list of solutions. On the other hand, if the characteristic polynomial has multiple roots, suppose the characteristic polynomial has roots say 1, 1, 2, 2, 2. Suppose we have a fifth order ODE and the characteristic polynomial happens to be m minus 1 the whole squared into m minus 2 the whole cube equal to 0. Then corresponding to the roots 1, 1, you have the solution e to the power x, x e to the power x. Corresponding to the triple root 2, you have the solutions e to the power 2x, x e to the power 2x, x squared e to the power 2x, and this will give you the complete list of solutions. More generally, one looks for solutions of the form p of x into e to the power mx. So you got in the earlier example that I gave where you got 1, 1, 2, 2, 2. So the solutions are e to the power x, x e to the power x, e to the power 2x, x e to the power 2x, x squared e to the power 2x. The most general solution is going to be a linear combination of these things, c1 plus c2x e to the power x, and then for the other one c3 plus c4x plus c5x squared e to the power 2x, and you will add these two, you will get the most general solution. So in this example, we have c1 plus c2x e to the power x, and then c3 plus c4x plus c5x squared e to the power 2x. So you got a polynomial times e to the power 2x, a polynomial times e to the power x. So you see the general solution is a form polynomial px times e to the power mx, and you take linear combinations of special solutions and you get all the solutions. Let's see how does this work for the case of a partial differential equation. Now we generalize this to the case of a partial differential equation with constant coefficient, such as the fundamental equations arising in physics. What are the fundamental equations that arise in physics? The Laplace's equation, the heat equation, the wave equation. So what is the heat equation? Del U by del T equals del 2U by del x squared. What's the wave equation? Del 2U by del T squared equal to del 2U by del x squared. Wave equation in one space dimension, the velocity of the wave is considered to be 1, just for simplicity. So now what you do is that since there are n independent variables x1, x2, xn, it's a partial differential equation. So it has n independent variables. You naturally will seek an exponential solution e to the power I times x1 chi1 plus x2 chi2 plus etc. plus xn chi-n, as you see displayed in 4.1. More general solutions can be obtained by taking linear combinations or superpositions. So now let us take the case of a wave equation, utt minus uxx equal to 0, equation 4.2 that is displayed in the slide. So what happens to 4.1? Here your x1 is t and your x2 is x. So your solution, your plane wave solution 4.1 is exponential of I times at minus bx. The solution 4.1 is called a plane wave. It's called a monochromatic plane wave and the frequency vector is chi1, chi2, chi-n. This should be familiar from physics, from wave propagation. Okay, so you're looking at equation 4.2, the wave equation, and you're feeding in exponential of I times at minus bx into 4.2. And what is the analog or the characteristic equation? The characteristic equation in this case is a squared minus b squared must be 0. So it has solutions a equal to plus minus b. So you can take lambda comma lambda or lambda comma minus lambda. A squared minus b squared equal to 0 has infinitely many solutions. It's a pair of lines, right? So the set of all points lambda comma lambda and the set of all points lambda comma minus lambda, they are all solutions of a squared minus b squared equal to 0. So now we would have to take a continuous superposition of plane waves. So what are our special solutions? Exponential of I lambda times x plus t, exponential of I lambda times x minus t. So now we got whole lot of special solutions. We have a one parameter family of special solutions. In the case of ODEs, we had only finitely many. If the characteristic equation is a polynomial in one variable, it has only finitely many roots, m1, m2, mk, and so the general solution was e to the power m1x c1 plus c2 e to the power m2x plus etc. plus ck e to the power mkx and so on. So there are finite linear combinations. Here we have to take infinite linear combinations. In fact, we have to take a uncountable linear combination or a continuous linear combination or a continuous superposition. What do you mean by continuous superposition? Continuous superposition means instead of a summation, we have to take an integral with respect to a density function f lambda. So we are looking at the most general solution of the wave equation is displayed in 4.4, integral minus infinity to infinity f of lambda exponential of I lambda into x plus t d lambda plus integral minus infinity to infinity g lambda, the other density function for the second family of solutions, into exponential of I lambda into x minus t d lambda, equation 4.4 that you see on the displayed slide. So this immediately tells us that we should be looking at integrals of the form minus infinity to infinity integral f of t e to the power minus it chi dt. You see these two integrals individually, how do they look? They look like a function f lambda multiplied by e to the power I lambda times a parameter x plus t or x minus t in the two pieces. So we are looking at these kinds of integrals. These kinds of integrals are called Fourier integrals. So let us make a definition. Definition 33. Suppose f is a function defined on the real line which is absolutely integrable. What do you mean by that? Integral minus infinity to infinity mod ft dt is finite. Then the integral minus infinity to infinity f of t e to the power minus I t chi dt is denoted by f hat of chi and is called the Fourier transform of f of t. That's what you see on the slide. Now there are several different conventions for the Fourier transform. Some people put, instead of e to the power minus I t chi, they take e to the power minus 2 pi I t chi. Some people put a 1 upon 2 pi factor in front of the Fourier transform. Some people put a 1 upon square root of 2 pi in front of the Fourier transform. There are all sorts of conventions, but we shall follow the convention that is common in the theory of partial differential equations, and we shall follow the book of Folland, Fourier analysis and its applications, and we will follow the convention that Folland follows, and I have given you a reference to page number 213 of this book. So this is the definition of a Fourier transform. Let us look at some simple examples. Number of exercises are displayed on the slide of calculating the Fourier transform. So let us take the function to be f of t equal to 1 when mod t less than or equal to 1 and f of t equal to 0 when mod t is bigger than 1. Evidently this function is absolutely integrable, it is a non-negative function and its integral from minus infinity to infinity is finite. We have to compute the Fourier transform of f. Okay, this is an easy exercise. What is the definition of Fourier transform? F hat of chi equal to integral over the real line f of t e to the power minus it chi. But f of t is 0 outside the interval minus 1 1 and in the interval minus 1 1 f is an even function. F is a constant function from minus 1 to 1, so f is an even function. And what is e to the power minus it chi? It is cos t chi plus I times sin t chi. The sine piece is an odd function and the cos is an even function. And so the odd function integral from minus 1 to 1 is 0. So only the even function will survive. And the integral of an even function is twice the integral from 0 to 1. So what you see on the slide is twice integral 0 to 1 cos of chi t dt. We can straight away integrate this. It becomes sin chi t by chi. Put in the limits 0 and 1. At the lower limit sin 0 is 0. At the upper limit you get sin chi by chi. So the Fourier transform of this function is what? Twice sin chi by chi. That was an easy exercise and I completely solved it. Take the second exercise. Compute the Fourier transform of the function given by f of t equal to 1 upon square root of 1 minus t squared when mod t less than 1 and 0 when mod t is bigger than or equal to 1. Again this function is integrable. It is a non-negative function on the real line and the integral from minus infinity to infinity is finite. Again it is an even function. Again you are going to get twice integral 0 to 1 cos chi t dt upon square root of 1 minus t squared. Now the problem is how to compute this integral. You cannot compute this integral in elementary terms. It is a Bessel function. Recall that in the very first module we have derived the integral representation for the Bessel's function. You need to go back and you have to identify this integral as a Bessel integral. I leave that part to you as an exercise. The third part is the Riemann-Lebag lemma. Let us recall what is the Riemann-Lebag lemma in the context of Fourier series. If you have an integrable function from minus pi to pi, then its Fourier coefficients ak and bk tend to 0 as k tends to infinity. Instead of Fourier coefficients, which is a discrete sequence, we have a Fourier transform f hat of chi. So the analog of Riemann-Lebag lemma is that when f is an absolutely integrable function on the real line, what happens to the Fourier transform? Mod f hat of chi goes to 0 as chi goes to plus minus infinity. You should try this Riemann-Lebag lemma yourself. If you cannot do it, we shall come back to it and we shall discuss this in detail. The next problem is to compute the Fourier transform of f of t equal to 1 upon a squared plus t squared. Again I have given you an even function. So it will be a Fourier cosine transform. The sine term will drop out. What will be the Fourier transform? Twice integral 0 to infinity cos chi t upon a squared plus t squared, or integral from minus infinity to infinity, ignore the factor of 2, integral from minus infinity to infinity cos chi t dt upon a squared plus t squared. How do you compute this integral? So let's continue with these exercises. Looking at the last two examples, what are you led to conjecture as a general result? What general result can you conjecture from the last two exercises? Take this function sin t by t. Is this an absolutely integrable function? Is it true that integral from minus infinity to infinity mod sin t by t dt converges? Answer is no. Sin t by t is not absolutely integrable. It is conditionally convergent, improper Riemann integral. It is not Lebag integrable. So, how do you even define the Fourier transform? Even the definition is suspect. Well, you can still define it. You can still say integral minus infinity to infinity sin t by t e to the power minus I chi t. But then these integrals will not be conditionally convergent. And when you are dealing with conditionally convergent integrals, you need to be very careful. And the next problem is to compute the convolution of two functions. I would like you to recall the definition of convolution, which you must have studied in your undergraduate course in connection with Laplace transforms. But again, we shall postpone this and return back to this later. Don't be too surprised if the convolution computation gets a little messy. And this is a very important example. This function FAT in probability theory has a very important name. It's called the Koshy distribution. It is called the Koshy distribution. So it plays a very important role in probability theory. Now let us come to our good old friend, the Gaussian. Already in the first module, we have calculated the Fourier transform of the Gaussian in connection with the Jacobi theta function identity. So already we have encountered this Fourier transform of the Gaussian right in the first chapter. So let us look at it again. This is one of the most important examples in the theory of Fourier transforms, and it's going to play a very crucial role in probability theory, number theory, quantum mechanics, theory of heat conduction and diffusive processes in general. The probability integral is one of the most important integrals. So the Fourier transform of e to the power minus at squared, it's an even function again. So what's the Fourier transform? Integral 0 to infinity twice e to the power minus at squared cos chi t dt. How did we calculate this integral in the first chapter? Call the integral I, differentiate with respect to chi, get a first order ODE for I, and we integrate this ODE and we get I. This was done in the very first module, and you must go back and review what we have done. So instead of repeating that thing all over again, I have given you the details here. Its I chi is this integral 4.6. You find a first order ODE for I chi. Instead of repeating all these calculations, we shall look at a second proof of this important result. Let us complete the square into 4.6. What's 4.6? It is exponential of minus at squared minus it chi. The last term is missing. Let us complete the square under the exponential. So let's do that. What do you get? It is exponential of minus a into t plus I chi by 2a the whole squared. So what have I added inside the exponential? An e to the power chi squared by 4a. I must compensate by putting the e to the power minus chi squared by 4a, and that's exactly what you see in the displayed equation 4.7. The integral I chi is e to the power minus chi squared by 4a integral minus infinity to infinity exponential of minus a into t plus I chi by 2a the whole square dt. It is very tempting to make a substitution. It is very tempting to say, let us put t plus I chi by 2a equal to y. Then straight away the integral becomes integral minus infinity to infinity e to the power minus ay squared dy, and you can quickly calculate it. You get the correct result, but the procedure is wrong. Procedure is terribly wrong. Nevertheless, you get the correct result, but this is unjustified. Can you explain why the procedure is wrong? What really goes wrong with it? Why is it illegal to put t plus I chi by 2a equal to y? Please think about this, and we'll return back to this in the next module. We shall apply Cauchy's theorem from complex analysis. So let us call this integral that you are trying to calculate. In 4.7 you are trying to compute the integral minus infinity to infinity exponential of minus a into t plus I chi by 2a the whole square dt. Call it j. Now look at the analytic function f of z equal to e to the power minus az squared. This function is analytic in the entire complex plane. It's an entire function. So take the closed rectangle from minus r to r along the real axis. The base of the rectangle is on the real axis. The rectangle has height chi upon 2a. So from r you go to r plus I chi by 2a. That's a vertical side. And then you return back parallel to the x-axis. R plus I chi by 2a to minus r plus I chi by 2a. And then you complete the rectangle drawing the other vertical side. Minus r plus I chi by 2a to minus r back to the x-axis. So this is a rectangle with vertices minus r, r plus I chi by 2a and minus r plus I chi by 2a. Call L1 the base of the rectangle and L2 the top side of the rectangle. The vertical sides are V1 and V2. What does Cauchy's theorem say? According to Cauchy's theorem, integral fz dz along L1 plus integral fz dz along L2 plus integral fz dz along V1 plus integral fz dz along V2 is 0. Now we must allow the r to go to infinity and see what happens. First of all, look at the base, integral fz dz along L1. It is an integral from minus infinity to infinity e to the power minus at squared dt. When r goes to infinity, that's exactly what you get. And this integral is root pi by root a, not a problem. Now, along the top side of the rectangle, you are integrating along a closed rectangle, or the boundary of a rectangle. In the base, you go from left to right. In the top side, you go from right to left. So the orientation is reversed. And so what happens to the top side of the rectangle? Integral fz dz along L2 is going to be minus the integral that you want. Namely, it is the integral that you are trying to compute. Exponential of minus a into t plus I chi by 2a the whole square dt. Except that you are going to put a minus sign there because you are trying to reverse the orientation. In other words, along the top side of the rectangle, you get minus j in the limit. What happens to the vertical sides? Integral fz dz along V1 and integral fz dz along V2 individually go to 0 as r goes to infinity, right? So now you get from equation 4.9, two terms drop out in the limit as r goes to infinity. The second term gives you the integral that you want with a minus sign, namely you get a minus j, and the first piece gives you root pi by root a. And so if you have computed j is exactly root pi by root a, and then we can see that the Fourier transform 4.7 is given by e to the power minus chi squared by 4a into root pi by root a. And that completes the computation of the Fourier transform of the Gaussian. Exercise: review the earlier procedure for calculating I chi via ODEs. The second problem is compute the Fourier transform of x squared e to the power minus ax squared, and more generally x to the power 2k e to the power minus ax squared. Now, to proceed further with the theory of Fourier transforms, we need to introduce a certain convenient space. We need a vector space V, and this space is called the Schwarz space script S of rapidly decreasing functions. And this space was introduced by Laurent Schwarz in his influential book on the theory of distributions. This function space, which is a vector space, has the advantage that it's a vector space, it's closed under differentiation and closed under multiplication by polynomials. Namely, if a function f of x is in this Schwarz space, then f prime of x is also in the Schwarz space. If you multiply f of x by a polynomial, it is again in the Schwarz space, and it's a vector space. So it has all the pleasant properties that you want Further, every function in this Schwarz space has the property that it is absolutely integrable, so you can calculate its Fourier transform. And also, this Schwarz space is big enough because if you take any function which is absolutely integrable, it can be approximated by elements in the Schwarz space. So, the space is particularly well suited to the study of the Fourier transform. One proves all the results in the context of this space and then one resorts to an approximation procedure. As long as you stick to this space S, there will be no technical problems. All technical problems disappear. You can differentiate under the integral sign as many times as you want. You can switch limits and integrals, and there are no technical issues, there are no technical hindrances when you work with this Schwarz space. So, it is a very convenient space to work with. And what we will do is that we will prove a theorem which is quite similar to a Parseval's formula which we derived earlier. And this result in the context of Fourier transform is called the Plancherel's theorem. So, let us define this space now. The space S consists of all infinitely differentiable functions f of t such that for any pair of natural numbers m and n, differentiate the function n times, multiply by the monomial t to the power m. This expression must be bounded. So, the supremum of t to the power m, nth derivative of f of t must be bounded. We immediately see that for any polynomial pt and any a bigger than 0, the function pt times e to the power minus at squared is in the Schwarz space. Easy exercises. Take the hyperbolic cosine, cosh at inverse. Cosh at inverse is in the Schwarz space. T times sinh at inverse lies in the Schwarz space for any a positive. So, I have given you two more members which are in the Schwarz space. Now, let us take the gamma function. The gamma function is defined for all complex values of z. For instance, let us restrict ourselves to the z in the right half plane. Gamma z with real part of z bigger than 0. That is perfectly well defined as an integral. So, that you have the gamma function. The gamma function is a analytic function in the right half plane, for instance. Now, let us restrict the gamma function to a vertical line. Let us restrict the gamma function to a vertical line and take its absolute value squared. Mod gamma a plus it the whole squared, where a is positive and t varies over the real line. So, as a function of t, this is going to be in the Schwarz space. This is a very important example of an element in the Schwarz space, but to prove that it lies in the Schwarz space, you will have to resort to the Stirling's approximation formula. You will need the Stirling's approximation formula to prove that this function is in the Schwarz space. It's an optional exercise.